Welcome back to BiochemSerye Learning on the Go. You're tuning into Podcast 2A, Carbohydrates, a sweet overview.
Definitely a sweet topic.
All right, let's dive into the fascinating world of carbohydrates. We're not just talking about those delicious donuts you might be craving. We're going deep into the molecules that fuel our bodies and play a crucial role in countless biological processes. And trust me, understanding these concepts is going to be way more satisfying than any sugary treat.
I agree. Much more satisfying.
Now, before we get lost in the details, let's start with the basics. What exactly are carbohydrates?
Yeah, that's a great place to start.
We've all heard of the simplified formula, CH2ON, and the term saccharides, which might ring a bell as sugars,
Right.
but it's really that simple. I mean, biochemistry is rarely straightforward.
You're absolutely right. While that formula gives us a general idea, some carbohydrates contain nitrogen, phosphorus, or sulfur, breaking the mold a bit. The key to understanding carbohydrates lies in their structure. Think of them as aldehyde or ketone derivatives of polyhydroxy alcohols. Now, I know that sounds like a mouthful, but it essentially means they are built from simple sugars, which are polyhydroxy alcohols, with a little extra something, either an aldehyde or a ketone group.
Okay, so we've got these basic building blocks. But why should our students, and let's be honest, we care so much about carbs. They're often demonized in diet fads, but they're essential for life, and not just for energy, right?
Exactly. Carbohydrates are way more versatile than people give them credit for, of course. They're a primary energy source. Think of glucose powering your brain as you're teaching or studying, but they're also stored as glycogen, providing that extra energy boost when you need it.
Speaking of energy, I definitely need my glucose after grading those exams.
Don't we all? But it's not just about energy. Think about the structural roles they play. Cellulose giving plants their rigidity. Chitin forming those tough exoskeletons of insects. It's amazing how these simple sugars can build such diverse and complex structures.
It's like nature's own Lego set. And let's not forget about dietary fiber, keeping things moving smoothly in our digestive systems. Plus, carbohydrates are components of DNA and RNA, the very blueprints of life.
You're hitting all the key points. And there's more. Carbohydrates are involved in cellular communication, lubrication, and even help our immune systems recognize invaders. They even play a role in detoxification. Some carbs, like glucuronic acid, act like our body's cleaning crew.
Wow, I think our students would be surprised to hear how many different hats carbohydrates wear in the body. But with so much variety, how do we even begin to classify these molecules? It's like trying to organize a library with millions of books.
We need a system, that's for sure. Think of it like a family tree. At the top, we have the monosaccharides, the parent sugars. These are the simplest forms, like glucose, fructose, and galactose.
Okay, so the monosaccharides are the foundation of the carbohydrate family. What comes next?
Next, we have the oligosaccharides, the siblings, which are short chains of monosaccharides linked together. Some familiar examples include sucrose, lactose, and maltose.
So if I'm understanding this correctly, sucrose, which we know is table sugar, is just glucose and fructose holding hands.
Precisely. And finally, we have the extended family, the polysaccharides. These are long chains of monosaccharides, sometimes hundreds or even thousands of units long. They can be linear or branched, and they often play structural roles or serve as energy stores. Think of starch in plants and glycogen in animals.
This family tree analogy is a great way to visualize the relationships between different types of carbohydrates. It's like a big family reunion. But let's zoom in on those monosaccharides, the parents of the carb family. What are the key things our students need to know about them?
First, the number of carbon atoms they have. We have trioses with 3 carbons, tetroses with 4, pentoses with 5, like riboses RNA, hexoses with 6, and heptoses with 7.
So it's like a numbering system based on carbon.
Exactly. And the second factor is whether they contain an aldehyde group, CHO, at the end of the carbon chain, making them aldoses, or a ketone group, C double bond O, within the chain, making them ketoses. This distinction is crucial because it affects their reactivity and how they interact with other molecules.
It's amazing how these small differences in structure can have such a big impact on their function. It's like changing one ingredient in a recipe can completely alter the taste of a dish. Now, with all these different monosaccharides, is there a rock star of the group, the one our students are most likely to encounter?
Without a doubt. It's glucose. It's the primary energy source for most living cells and plays a central role in numerous metabolic pathways. It's like the celebrity of the carbohydrate world. Everyone knows its name.
So glucose is the A-lister of the carbohydrate world, but why is it so important? What makes it the go-to energy source?
Well, glucose is readily available and easily metabolized. Our bodies have evolved efficient mechanisms for breaking it down and extracting energy. And it's versatile in its structure, too. It can exist as a straight chain. But it's more commonly found in a ring structure in solution. This ring structure influences its reactivity and how it interacts with other molecules.
So it's not just a simple sugar, it's a dynamic molecule with a complex personality. I bet our students would be surprised to learn that. Speaking of complexity, you mentioned that glucose can exist in different forms, even though its chemical formula remains the same. Is that what isomerism is all about?
You got it. Isomers are molecules with the same molecular formula but different structural arrangements. It's like using the same set of Lego bricks to build different structures.
That's a great way to explain it. So how does this apply to carbohydrates? What kind of variations are we talking about?
Well, one type is ketose-aldose isomerism. Remember how we talked about aldoses and ketoses having different functional groups? Glucose and fructose are a classic example. They have the same formula, C6H12O6. But glucose is an aldose, while fructose is a ketose. That small change in the functional group leads to different properties and metabolic fates.
So even though they have the same building blocks, their arrangement gives them unique identities. That's fascinating. And it's crucial for our students to understand this because it affects how our bodies process these sugars.
Exactly. Another important type of isomerism is D and L isomerism. This one gets a bit more into the 3D world of molecules.
Okay, I'm ready to put on my 3D glasses.
Imagine holding your hands up with your thumbs pointing in opposite directions. That's like D and L isomers. They're mirror images of each other. This handedness is determined by the orientation of a specific hydroxyl group.
Oh,
On a particular carbon atom.
like looking in a mirror. So one is left-handed and the other is right-handed. Does that affect how they function?
Absolutely. Most naturally occurring sugars, like the glucose our bodies use, are D-isomers. Enzymes, the workhorses of our cells, are very specific and often only recognize one form.
So even though they're mirror images, they can behave differently in biological systems. That's a key point for our students to grasp.
Precisely. And this mirror image concept is related to another type of isomerism, optical isomerism. Some isomers can rotate polarized light, making them optically active. They're like tiny molecular prisms, bending light in specific directions.
Okay, this is where it gets a little mind-bending. So we have isomers rotating light. Are there different degrees of rotation?
Yes. Some isomers rotate light to the right, called dextrorotatory or plus, while others rotate it to the left, called levorotatory or minus. And if you have an equal mixture of both, their rotations cancel out. And the mixture has no overall optical activity. We call that a racemic mixture.
It's like a molecular tug-of-war with light.
Now, there are two more types of isomerism worth mentioning, epimerism and anomerism. Epimers are isomers that differ in configuration around just one specific carbon atom, other than the anomeric carbon.
So they're almost identical. But those tiny differences can matter in biochemistry, right?
Absolutely. For example, glucose, galactose, and mannose are all hexoses, but they differ slightly in the arrangement of atoms around specific carbon atoms. Those subtle differences can have a big impact on how they interact with enzymes and other molecules.
It's like a single genetic mutation can lead to significant changes in an organism. Small changes can have big consequences.
Exactly. And finally, we have anomerism. This arises due to the ring structure of sugars. Remember how we talked about glucose forming a ring? Well, when that ring forms, a new asymmetric carbon atom is created.
So closing the loop creates a new point of variation.
Precisely. This new asymmetric carbon can have two different configurations, leading to alpha and beta forms. It's like a slight twist in the ring. But it can influence how these sugars interact with other molecules, particularly enzymes.
So even in their ring forms, sugars can still have variations. It's like they're constantly keeping us on our toes. I bet this will keep our students on their toes, too. Speaking of twists and turns, what about mutarotation? I've heard the term, but I'm not quite sure I fully understand it.
Mutarotation is fascinating. It highlights how dynamic sugar molecules are in solution. Imagine the alpha and beta forms of a sugar constantly switching back and forth like they're changing dance partners.
So they're not fixed in one form, they're constantly interconverting? That's pretty wild.
It is, and this interconversion actually leads to a change in optical rotation over time until an equilibrium is reached.
So it's not a static picture. These molecules are in constant motion, like they're doing a little dance in the solution.
Precisely. And not all sugars can participate in this dance. Non-reducing sugars, those without a free anomeric OH group, are kind of stuck on the sidelines. They lack the necessary partner for this interconversion.
So it's like having two left feet in the molecular world. I'll have to remember that one for class. Okay, we've explored the structure, and different forms of monosaccharides. But what about their reactivity? How do they interact with other molecules and participate in those important biochemical processes?
That's a great question. And it's crucial for understanding how carbohydrates function in living organisms. Monosaccharides are quite reactive, and their chemical transformations are essential for life.
Okay, let's dive into the nitty-gritty of sugar chemistry. What happens when these monosaccharides encounter strong acids? I'm sure our students will need to know this for their exams.
When monosaccharides react with strong acids like sulfuric or hydrochloric acid, they undergo dehydration, losing water molecules and forming furfural derivatives.
So it's like squeezing the water out of them and creating a new type of molecule. What happens to those furfural derivatives?
Those furfurals are quite handy. They react with certain reagents to produce colored complexes. And this is the basis for several sugar identification tests, like Mullish's test, Seliwanoff's test, Bial's test, and even the Toland's fluoroglucinol HCl test.
Ah, so it's like a color-coded system for identifying different sugars.
Yeah.
That's a great visual for our students to remember. Now let's shift gears and see what happens when monosaccharides encounter alkalis or bases. How do sugars react differently in a basic environment?
Well, alkalis cause a fascinating process called enolization, essentially. The sugar molecule rearranges itself to form an enediol, which has a double bond and two hydroxyl groups attached to the same carbon atom.
So it's like a molecular makeover,
Yeah.
creating a new reactive center.
Yeah.
What's the significance of this enolization?
This is where it gets really interesting. These enediols are highly reactive, making the sugar a powerful reducing agent. Tests like Benedict's test and Feeling's test, which are commonly used to detect sugars in clinical settings, rely on this reducing property.
So these tests exploit the enediol's ability to donate electrons. That's a key concept for our students to understand, especially those going into healthcare fields.
Absolutely. And here's a fun fact. Through enolization, glucose, fructose, and mannose can actually interconvert in a dilute alkaline solution. It's like they're molecular chameleons, shifting their forms depending on the environment.
Wow. So even though they have distinct structures, they can transform into each other under certain conditions. That's amazing.
It is. Now moving on to another important reaction, oxidation. What happens when sugars lose electrons?
Let's explore that. Oxidation is like adding a little bit of oxygen power to the sugar molecule, right?
You could say that. Depending on the oxidizing agent and the conditions, an aldose like glucose can be oxidized in a few different ways, resulting in a variety of sugar acids.
Okay, so oxidation can lead to the formation of different sugar acids. Can you give us some examples? I'm sure our students would appreciate some specific cases.
Certainly. For instance, using a mild oxidizing agent like hypobromous acid, HOBr, leads to the formation of aldonic acids. So glucose would be oxidized to gluconic acid.
So it's a subtle tweak to the sugar molecule, adding a carboxyl group.
Exactly. But if we use a stronger oxidizing agent like nitric acid, we can take things further. Nitric acid oxidizes both the aldehyde group and the terminal primary alcohol group, converting them both to carboxyl groups. This forms saccharic acid.
So it's like a double whammy of oxidation, affecting both ends of the sugar molecule.
Precisely. And one more type of oxidation is worth mentioning, the formation of uronic acids. This is where oxidation specifically targets the terminal primary alcohol group, leaving the aldehyde group intact.
So it's a selective oxidation, targeting a specific part of the sugar molecule. These different types of oxidation reactions certainly add another layer of complexity to the world of carbohydrates. So we've covered oxidation. But what about the opposite process, reduction? What happens when sugars gain electrons? I'm sure our students will be asked about this on their exams.
Reduction is essentially the reverse of oxidation. Instead of adding oxygen, we're adding hydrogen, leading to the formation of sugar alcohols.
So it's like hydrogenating the sugar. I've heard that term used with fats.
You're making great connections. And just like with fats, the addition of hydrogen can change the properties of the molecule. Some sugar alcohols like xylitol and sorbitol are used commercially as sweeteners.
So those sugar-free candies and gum probably contain sugar alcohols.
Very likely. And some sugar alcohols are even used in medical settings as osmotic diuretics or laxatives.
Wow. So those seemingly simple sugar alcohols have a surprising range of applications. Now, one last reaction I'm curious about is the action of phenylhydrazine. What happens when sugars encounter this compound?
This reaction is a classic one in carbohydrate chemistry and leads to the formation of usazones.
Usazones. What makes them special?
Usazones are crystalline derivatives of sugars that are incredibly useful for identifying and characterizing different sugars. You see different sugars react with phenylhydrazine in slightly different ways, producing ozozones with distinct shapes and melting points.
So each sugar has its own unique fingerprint in the form of an ozone. That's brilliant.
Exactly. It makes ozone formation a valuable tool for distinguishing between sugars that might otherwise be difficult to tell apart.
It's amazing how these seemingly simple reactions can be used to unlock the secrets of sugar structure and identity. I think our students will appreciate knowing this. We've certainly covered a lot of ground in this exploration of monosaccharides. It's clear that these seemingly simple sugars are anything but simple, from their diverse structures and isomeric forms to their reactivity and involvement in numerous biological processes. Monosaccharides are truly the building blocks of the carbohydrate world. Now let's move on to the siblings in our carbohydrate family, the disaccharides. These are formed when two monosaccharides, our parent sugars, link together. What are some of the most common disaccharides our students will encounter, and how are they formed?
That's a great question. And it leads us directly to the fascinating world of glycosidic bonds. Disaccharides are formed when the anomeric hydroxyl group of one sugar reacts with hydroxyl group on another sugar. This forms a special bond called a glycosidic bond, and it's the key to linking those monosaccharides together.
So it's like those two monosaccharides are reaching out and shaking hands, forming a strong connection through this glycosidic bond. But what determines which sugars link up and in what orientation? I'm sure our students will be curious about that.
You're right. The formation of these glycosidic bonds is very specific, and it depends on the enzymes involved and the configuration of the sugars. For instance, sucrose, which we all know as table sugar, is formed by linking glucose and fructose in a very specific way.
Ah, so it's not just any random connection. It's a carefully orchestrated molecular dance. But what about other disaccharides, like lactose and maltose? What makes them unique?
Lactose, the sugar found in milk, is made up of glucose and galactose linked together, and maltose, which is formed during the breakdown of starch, is actually made up of two glucose units.
So it's all about different combinations of those basic monosaccharide building blocks, linked together in specific ways. I can see how this could get complex quickly, but it also highlights the incredible diversity of the carbohydrate world.
Exactly. And the type of glycosidic linkage can dramatically influence the properties of the disaccharide. For instance, sucrose is a non-reducing sugar because the glycosidic bond involves both anomeric carbons. This prevents it from opening up into that linear form we talked about earlier.
So it's like they're holding hands so tightly that they can't let go and open up. That's a great visual.
In contrast, lactose and maltose are reducing sugars because they have a free anomeric carbon that can participate in those redox reactions we discussed earlier.
So it's like one of their hands is free to shake hands with other molecules.
Precisely. And these differences in reducing properties are used to distinguish between different disaccharides in laboratory tests.
Okay. I'm starting to see how these subtle structural differences can have a big impact on the behavior of these carbohydrates. Now, we've talked about monosaccharides and disaccharides, but what about those large, complex carbohydrates, the polysaccharides? They're like the extended family of the carbohydrate world, gathering for a big family reunion. What are some examples of these complex carbohydrates, and what roles do they play?
You're right. Polysaccharides are the real heavy hitters in the carbohydrate world. They're polymers made up of many monosaccharide units linked together by those glycosidic bonds we talked about. They can be linear, like a long chain, or branched, like a tree with many branches.
So they're like long chains of sugars, all holding hands. And I imagine they play a wide variety of roles, given their size and complexity.
You're absolutely right. Polysaccharides are involved in everything from energy storage to structural support.
Okay, let's talk about energy storage first. What are some examples of polysaccharides that store energy?
Well, the most well-known example in plants is starch. Starch is actually a mixture of two polysaccharides, amylose, which is a linear chain of glucose units, and amylopectin, which is branched.
So plants store their energy as long chains of glucose, just like we store energy as glycogen.
Precisely. And when plants need energy, they break down starch into glucose, which can then be used for various metabolic processes.
Makes sense. But we don't store starch, right? We use glycogen. What's the difference between starch and glycogen?
We don't store starch, but we have a similar polysaccharide called glycogen. Glycogen is also made up of glucose units, but it's much more highly branched than amylopectin.
So it's like a super branched energy storage molecule. Why is glycogen so branched?
Good question. The branching allows for faster breakdown and release of glucose when our bodies need energy quickly.
Ah, so it's like having multiple access points to the stored glucose. That makes sense, especially when we think about the energy demands of muscle activity.
Exactly. We store glycogen primarily in our liver and muscles. ready to be mobilized when needed.
It's like having our own personal energy reserves, ready to fuel our activities. Now, apart from energy storage, polysaccharides also play crucial structural roles in living organisms, right? I'm thinking about cellulose in plants.
You're right on track. Cellulose is the most abundant structural polysaccharide on Earth. It's the main component of plant cell walls, giving plants their rigidity and strength.
So that's what gives trees their sturdy trunks and leaves their shape. I always wondered about that.
Exactly. Cellulose is a linear polymer of glucose units, just like starch. However, the glycosidic bonds in cellulose are different, making it indigestible to us.
So we can't break down those bonds to access the glucose in cellulose. That's why we can't digest wood.
That's right. That's why cellulose acts as dietary fiber, providing bulk and promoting digestive health.
It's amazing how a slight difference in bond structure can make such a big difference in our ability to digest these carbohydrates. I bet our students will find that fascinating.
And another fascinating structural polysaccharide is chitin. Chitin is found in the exoskeletons of insects, crustaceans, and other arthropods, providing them with protection and support.
So it's like nature's armor plating.
Exactly. Chitin is similar in structure to cellulose, but it contains a nitrogen-containing group, making it more rigid and durable.
It's amazing how nature has evolved such diverse and specialized polysaccharides for different functions.
Now, apart from starch,
Yeah.
glycogen, cellulose, and chitin, there's a whole world of other polysaccharides out there, each with its unique structure and function.
Okay, what are some examples of these other polysaccharides? I'm sure our students will be curious to learn about them.
Well, one interesting group is the glycosaminoglycans, also known as mucopolysaccharides. These are long, unbranched polysaccharides that contain repeating disaccharide units, often with amino sugars and uronic acids.
So they're like complex chains of sugars with some extra functional groups thrown in.
Exactly. And glycosaminoglycans are often found in connective tissues, providing lubrication, cushioning, and structural integrity.
So they're like the shock absorbers of our bodies.
That's a great analogy. For instance, hyaluronic acid, a type of glycosaminoglycan, is found in our joints, providing lubrication and cushioning. It's also used in cosmetics to plump up the skin.
So that's why hyaluronic acid is such a popular ingredient in skincare products. I knew it had something to do with carbohydrates.
Precisely. And another important glycosaminoglycan is heparin. Heparin is a natural anticoagulant, preventing blood clots from forming. It's often used medically to treat deep vein thrombosis and pulmonary embolism.
Wow, so those glycosaminoglycans have some pretty important medical applications. I bet our students will be intrigued by them.
Yeah, they are. And there are many other fascinating polysaccharides out there, such as dextrins, pectins, and agar, each with its own unique properties and applications. The world of carbohydrates is vast and diverse, and we've only just begun to explore it.
Okay, I'm starting to see how these polysaccharides, the extended family of carbohydrates, are real workhorses in biological systems.
Yeah.
They're not just about storing energy, they're involved in structural support, cell signaling, and even medical applications. It's impressive how diverse and versatile they are.
Absolutely. And we haven't even touched on the fascinating world of glycoproteins and glycolipids yet. Remember those name tags and signposts we talked about earlier?
Good.
That's where these complex molecules come into play.
Ah, yes, the sugar-coated molecules that play a crucial role in cell signaling and recognition. I'm eager to learn more about how these glycoproteins and glycolipids are formed, and what makes them so important.
Well, it all comes back to those glycosidic bonds we discussed. Glycoproteins are formed when carbohydrates are attached to proteins, and glycolipids are formed when carbohydrates are attached to lipids. It's like decorating these molecules with intricate sugar patterns.
So it's not just a random attachment, it's a specific and controlled process. How does this cell know which sugars to attach and where to attach them?
That's a great question. And it's a key area of research in glycobiology. The process of adding carbohydrates to proteins and lipids is called glycosylation. And it's a highly regulated and complex process. Specific enzymes called glycosyltransferases are responsible for catalyzing the formation of those glycosidic bonds, ensuring that the right sugars are added in the right places.
So it's like a highly skilled molecular artist,
Hmm.
carefully painting these intricate sugar patterns onto proteins and lipids. What are some of the key roles these glycoproteins and glycolipids play in the body?
They're involved in a wide range of processes, from cell recognition and adhesion to immune responses and even fertilization. For instance, glycoproteins on the surface of red blood cells determine our blood type.
So that's why blood transfusions have to be carefully matched. It all comes down to those sugar patterns on the red blood cells.
Exactly. And in the immune system, glycoproteins play a crucial role in recognizing and targeting foreign invaders. The specific sugar patterns on the surface of pathogens, like bacteria and viruses, act as red flags that alert our immune cells to their presence.
So those sugars are like the wanted posters of the molecular world, helping our immune system track down and eliminate those unwanted guests.
That's a great analogy. And glycolipids,
Mhm.
particularly those found in nerve tissue, are important for nerve impulse transmission and brain development.
So those carbohydrates are helping our brains wire up correctly. That's incredible.
It is. The world of glycobiology is vast and still largely unexplored. But we're learning more and more about the crucial roles that carbohydrates play in these complex molecules.
This has been an eye-opening journey into the world of carbohydrates. We've covered so much ground, from the basic building blocks of monosaccharides to the complex structures of polysaccharides and glycoproteins. And we've seen how these seemingly simple sugars are involved in countless biological processes, from energy storage to cell signaling and immune responses. It's truly remarkable.
It is, and I hope our listeners, whether they're students, fellow professors, or anyone with a curious mind, have gained a newfound appreciation for the amazing world of carbohydrates.
I think they will. Now, to help solidify their understanding, let's wrap up this episode with 10 key questions and answers to test their knowledge and highlight the essential concepts we've covered today.
Sounds like a great plan. Let's see if they've been paying attention.
All right, are you ready for a pop quiz to test your carbohydrate knowledge?
Let's do it. It's time to see if our listeners have been paying attention.
Okay, question number 1. What is the basic empirical formula that represents the ratio of carbon, hydrogen, and oxygen atoms commonly found in carbohydrates?
Think back to the beginning of our deep dive. Remember that simple formula that gives us a general idea of what carbohydrates are made of?
The answer is CH2ON. This formula highlights the common building blocks of carbohydrates: carbon, hydrogen, and oxygen.
All right, question number 2. Carbohydrates are incredibly versatile molecules. Can you name 3 important functions they perform in living organisms?
This one's a bit of a freebie. We've talked about so many amazing roles carbohydrates play.
Here are a few examples. They act as an energy source, providing fuel for cellular processes. They store energy in the form of starch in plants and glycogen in animals. They also serve as structural components, like cellulose in plant cell walls and chitin in insect exoskeletons. And don't forget their roles in dietary fiber, DNA and RNA composition, cellular communication, and even detoxification.
Carbohydrates are the true multitaskers of the molecular world. Okay, question number 3. Remember our carbohydrate family tree. What are the 3 main classes of carbohydrates based on the number of sugar units linked together?
Think about those family gatherings. We have the parents, the siblings, and the extended family.
The answer is monosaccharides, the single sugar units, oligosaccharides, short chains of sugar units, and polysaccharides, long chains of sugar units.
Okay, on to question number 4. What is the key difference between an aldose and a ketose? Hint, it has to do with the position of a particular functional group.
Remember those aldehydes and ketones from organic chemistry?
The answer lies in the position of the carbonyl group. C, double bond O. Aldoses have the carbonyl group at the end of the carbon chain, aldehyde group, while ketoses have it within the carbon chain, ketone group. This seemingly small difference affects their reactivity and how they interact with other molecules.
Question number 5. Why is glucose considered such an important monosaccharide? What makes it so special?
Think about what fuels your brain power and keeps your cells running.
The answer is that glucose is the primary energy source for most living cells. Our bodies have evolved efficient ways to break down glucose and extract energy from it, making it a vital molecule for life.
Let's move on to question number 6. Remember those molecular Legos we talked about? Define the term isomer in the context of carbohydrates.
Think about rearranging those building blocks to create different structures.
Isomers are molecules that have the same molecular formula but different structural arrangements. This means they have the same number and types of atoms. But those atoms are connected in different ways, leading to variations in their properties and functions.
Question number 7. What is the difference between D-glucose and L-glucose? This one delves into the 3D world of molecules.
Remember those mirror images we talked about, like your left and right hands?
D-glucose and L-glucose are enantiomers, which means they are non-superimposable mirror images of each other. The difference lies in the orientation of a specific hydroxyl group
OH.
on a particular carbon atom. Most naturally occurring sugars are D-isomers.
All right, question number 8. What is mutation, and why is it important for understanding the behavior of sugars in solution?
Think about those alpha and beta sugars doing a little dance in solution.
Mutarotation is the change in optical rotation that occurs when the alpha and beta anomers of a sugar interconvert in solution. This happens because the ring-formed sugars can open up into a linear form and then reclose, forming either the alpha or beta anomer.
Question number 9. What is the significance of enolization in carbohydrate chemistry? Hint. It has to do with the reactivity of sugars.
Think about those enediols and their ability to donate electrons.
Enolization makes sugar strong, reducing agents. Enediols, formed during enolization, are highly reactive and can readily donate electrons, which is the basis for several important tests used to detect sugars.
And for our final question, number 10, name 2 chemical tests that rely on the reducing properties of carbohydrates. These are commonly used in clinical settings.
Think about those tests that exploit the sugar's ability to donate electrons and change color.
2 common tests are Benedict's test and Fehling's test. These tests rely on the ability of reducing sugars to reduce other compounds, resulting in a visible color change that indicates the presence of sugar.
Well, there you have it. 10 key questions to test your carbohydrate knowledge. We hope you aced this pop quiz and are walking away with a newfound appreciation for the amazing world of carbohydrates.
It's been a pleasure diving into the sweet world of carbohydrates with you all. Until next time, keep those brains buzzing and those metabolic pathways humming.
Thanks for joining us on BiochemSerye Learning on the Go. We'll see you next time for another deep dive into the fascinating world of biochemistry.